Hello friends, my name is Steven, and today I'm going to be doing a crash course in Econ 382, aka Economic Theory for Cuties, okay? Today is going to be a long video, and we're going to cover a lot of topics. I'm not going to go into super detail into all the topics, because I'm going to be overviewing everything. Every topic that you can find in Econ 382, at least in most of these classes, we're going to talk about. And it's a class about how imperfect competition is introduced into our world, and more realistic scenarios than we dealt with in 380. So let's get into it. All right, there's a lot to cover. In 380, you left off with general equilibrium. No, sorry, you left off with partial equilibrium. We're going to talk about general equilibrium now. What's the difference? Well, in partial equilibrium, you have prices given to you, right? You had some function of utility that was a function of x and y, and that led you to get x and y star. Right? And you got that in terms of income and prices, income and px, py, and you might have had a production function as well, and you had, wage and the rental rate. And all these things were given to you, your income, your price of x, your price of y. Well, you assumed that your income was equal to your consumption, but px, py, w, and r, those were all given to you. And now we're going to work with relative prices. Relative prices, meaning we can normalize one of these prices. Normalize, well, we'll just say like, oh, how about r equals 1? Okay, or py equals 1. And when we normalize these prices, then we can get everything else in terms of relative prices. And we can actually solve for the entire market for everything else, because we're looking at how these markets interplay with each other and how interdependent they are. In Econ 380, you had some indifference curves. Here's x, y, here's a consumer with some indifference curves. Boom, ba boom, ba boom, right? And that's pretty good. We'll call this person Phineas, okay? So Phineas has some indifference curves there. Econ 382, let's observe two consumers. Back to back, all right? We'll call the other one Ferb, and we'll take Ferb's indifference curves, and we'll lay them out on this same graph by just flipping it upside down right here. This is Ferb, and saying, okay, here's Ferb's indifference curves. He's just, he's just upside down, just like that. All right, well, Phineas and Ferb exist in this. We can do this because we have this closed exchange economy. So there's a set amount of x and a set amount of y, and Phineas and Ferb are endowed with some x and some y. All right, we're going to give some to Phineas, we're going to give some to Ferb. And their income, we're going to define Phineas's income as the value of the endowment he's given. Okay? So the income of Phineas, and it's the same thing for Ferb, is going to be the amount of x that he's endowed with, times the price of x, that's how much it values at, and then how much y he's endowed with, times the price of y. All right, that is Phineas's income, the value of his endowment. And the same thing for Ferb, okay? It's endowed with some amount of x, and then Ferb has the rest, because they're in this closed exchange economy. All right, so they'll exchange with each other. They will trade to some point, let's call it this point right here, where they have some amount of x and y. They've traded to such a point where, notice that one person cannot be made better off without the other person being made worse off. So they try to get to the highest indifference curve possible, and that's where they end up. And it could be at a different point. Let's say, their allocations were such, maybe we started with the allocation over here or something, and they traded until Phineas is right there, and Ferb is right there, and they trade to that point. Notice that's a point where one person cannot be made better off without the other person being made worse off. Okay, it's efficient. It's not equitable, because Ferb has a lot less than Phineas in this case. So, but even though it's not equitable, it is efficient. Okay, so we call that Pareto efficiency, by the way, when one person cannot be made better off without the other person being made worse off. And we'll assume there's some, let's say there's some set of points. There's an infinite set of points that are Pareto efficient. Possible points that they could trade and end up at one of these points. Now, interesting thing about this this curve, we'll call this a contract curve, contracts between Phineas and Ferb. And this contract curve, the first fundamental theorem of welfare economics says that every perfectly competitive outcome is Pareto efficient, which is just like, that's just the invisible hand. We already knew that, right? In a perfect competition, your outcome is efficient. All right, got it. Every perfectly competitive outcome will be somewhere on this contract curve. Now, the second fundamental theorem of welfare economics says that any point on this curve, pick a point, any point, I can reach that point by just redistributing the initial endowments and then letting Phineas and Ferb trade. All right, so every point on this contract curve, every Pareto efficient point can be viewed as just a redistribution of the initial endowments. I snatch them up and then I redistribute them in such a way that they will end up at some Pareto efficient point that I choose. And all of these points can be achieved by that. And that's the second fundamental theorem of welfare economics, okay? So that's how that works out. Now, let's go back to this X, PX, PY stuff. So in this exchange economy, we have, for our equilibrium, two market clearing conditions. Here's our market clearing conditions. We have, let's get rid of this. Don't need any of this stuff. Okay, so we have X supplied equals X demanded. And can you guess the next one? Y supplied equals Y demanded. Those are our two market clearing conditions. Well, we know what X supplied is. It's the amount endowed to Phineas plus the amount endowed to Ferb, right? So X supplied is a given here, right? And X demanded, notice, if they both had a pretty standard Cobb-Douglas function, then we might find, that Phineas's X demanded is income over 2px, right? But notice in this situation, income is given in terms of the endowments, which we already know, and px and py. And we already talked about how in general equilibrium, we normalize one of these prices. The only prices we have here are px and py. So if we normalize py to 1, then we just have px here. That's our unknown, right? So we have px and income. And so if we solve here, notice that our market clearing condition suggests that we just have to find px. But then we've solved for everything in our economy. What I'm saying is we didn't even need the second equation. We could have just had this equation and solved the whole thing, right? General equilibrium, done. We're done with this exchange economy. So this equation is actually redundant. And this is Walras's law, right? There's a guy, Walras, that said, when you have n1 minus 1 of your markets clear, then the nth one clears trivially. In the case, if we know that our X market is in equilibrium, then the Y market has to be in equilibrium. That's just given, all right? Okay, because we already solved everything else. Okay, that's Walras's law. That's what that says. So okay, exchange economy, all that stuff is brilliant, but it's really simple. Okay, and we want to, in normal real life, people are not endowed with just goods X and Y that they can exchange. Not on some like island somewhere. Instead, it's a little more realistic to assume that they're endowed with capital and labor. Okay, so we're going to change the endowments. In fact, forget all of this exchange economy stuff. Don't worry about any of that. So let's say we have one representative agent. Forget about Phineas and Ferb. We'll have one consumer that's going to represent the entire economy, and they're going to be endowed. Their income is going to be the value of their endowment, which is the value of the labor they're endowed with, plus the value of the capital that they're endowed with. Okay. Income equals the value of their endowment of labor and capital. Pretty simple. That's the wage rate, that's the rental rate, labor and capital. Perfect. And then we're going to have a firm. We're going to have a representative firm, and they're going to produce two goods, X and Y, and they're going to have some production function for those, which are functions of labor and capital, right? So they have that for Q. I'll just write X here, but they have it for Y too, okay? But I'm going to focus on just one good, and it applies to the other good as well. So in these cases, okay, so you have a firm with a production function, and you have a consumer, representative consumer, with a utility function. That's a function of X and Y. Okay, so what we know is that in this case, we have 4 market clearing conditions. Yes, we have 4. We have that the labor supply equals the labor demanded. The capital supplied equals the capital demanded. We have X supplied equals X demanded, and Y supplied equals Y demanded. Now, Walras's law still hold. If n minus 1 markets clear, then the last one trivially has to clear. Okay, mathematically, that's just how it works out. Now, we also have these prices, W, R, and PX, and PY. Those are our prices. So, again, we are going to normalize one of these prices for general equilibrium so that we can get the rest in terms of relative prices, okay? Let's choose R. We're going to say R equals 1. Okay, we're normalizing R. The rest is prices in terms of R, okay? Perfect. Now here's how you solve a general equilibrium problem with production. You're going to take the firm, and the firm side, they're going to cost minimize. And when they cost minimize, we know from 380, they'll get some conditional factor demands, L and K. Those are going to be in terms of Q, W, and R. Okay, perfect. Cost minimization done. Now you're going to, for the consumer side, you're going to utility maximize. And then you're going to get X star and Y star. Those are demands for X and Y. And those are going to be in terms of, as we know, income and prices. But what is income? Income is in terms of input prices, W and R, and your initial endowments. So X star and Y star are going to be in terms of your initial endowments, and then input prices, and then output prices. Okay, so we solved the firm side. We solved the consumer side. Now, what we're going to do is we're going to invoke the magic assumption of perfect competition and say that price equals marginal cost. Or in other words, the price of X is the marginal cost of X. So I have some cost function for this firm up here, and a cost function for X. So I find the marginal cost, I set it equal to PX, and I do the same for Y. Again, I'm doing all of this for Y as well. So now I've solved for PX and PY. So now I get rid of those, and I just have my unknowns as, well, I already normalized R to 1 as well. Now I just have W and Q as my unknowns, right? And so now I'm going to set labor demand equal to labor supply and invoke my market clearing condition. And now notice that I can take, what is Q? Well, my Q demanded I already solved in terms of X star and Y star, right? So I just plug that in. So when I set my market clearing condition as labor demand equals labor supply, I now have everything I need to solve for my last unknown, which is W. Okay, so I solve for W, and boom, I have solved my general equilibrium. And of course, I do the same thing for X and Y. I do the same thing for labor and capital. Okay, so that's how you solve a general equilibrium with production. Now, interestingly enough, let's say that there is only one input. Let's forget labor and capital. Let's just say labor is the only input. So we have some simple production function. Let's say that this firm has production of X is going to equal labor devoted to X to 1/2, and Y is going to be similar. Okay, and let's say that the total amount of labor in the economy is 100. Okay, so in this case, then I can just solve really easily for my factor demands. Lx star is going to be, as you can see, Qx squared. Ly star is going to be Qy squared. And if supply equals demand, then 100 is going to equal Qx squared plus Qy squared, yeah? Okay, perfect. Well, that is pretty graphable. Doesn't that look graphable to you? So we can graph that. Here's X, here's Y, and there you go. There's a PPF right there, all right, in terms of X and Y. We solved that just from our one input. We can do that because we have one input. So we're just looking at the trade between, or the trade-offs between X and Y that this firm can make. And then you're going to have, some consumer with a utility function in terms of X and Y. If we maximize that utility, we'll see that the indifference curve from the consumer will go, and it'll be tangent to some point here. And boom, we know, obviously, that the MRS for the consumer is equal to the price ratio. We know that the marginal rate of product transformation is also going to be equal to the price ratio on our PPF, right? So they're both going to be equal to that price ratio right there. These are actually equal to each other. So boom, that is the one input case. Pretty simple stuff. If you had trade there, now that would change things a little bit. So with trade, basically you have some world price that is messing things up, and you got this world price ratio. Let me draw this new price ratio right here. It'll go down like that, yeah? So that represents our constant world price ratio. Notice that production then is going to happen right here. So these are still true, but independently of each other, right? The MRS does not equal to MRPT anymore. Oh, by the way, the MRPT, if you forgot, is negative dy dx. Yeah, anyway, so they're going to produce right here, right, where the MRPT equals the world price ratio. And then the MRS is also going to equal the world price ratio, but notice that consumers are probably going to consume right there, right? So they're consuming more X and Y, and it's going to be different from what you produce. You're producing in your local economy, you're producing less X and more Y when you invoke a world price in there. So that's how trade interacts with everything. And okay, but enough of this general equilibrium stuff, all right? That's all perfect competition related, and we're not here to talk about perfect competition, okay? Okay, what is perfection? That's not something that we have currently in this world. So instead, we are going to talk about what goes wrong in perfect competition. Okay, so not wrong, just different. The assumptions just don't hold. Okay, I like to think that in perfect competition, markets function perfectly. Whoa. No hiccups found. Okay? What does this mean? We have many buyers and sellers with free entry and exit. They have perfect information. All the buyers and sellers, perfect information. There's no externalities. They have homogeneous private goods, and there's frictionless markets. Okay? So what does that mean essentially like in function? Well, if you have many buyers and sellers with free entry and exit, then you have no market power. No one buyer or seller, or even groups of buyers or sellers, has ability to influence the price. Okay, they're all price takers, no market power, perfect information about prices, perfect information about each other's characteristics, each other's payoffs. They have no externalities. What do we want to say about that? There's just no externalities. I mean, they bear the full costs and benefits of their decisions. Homogeneous private goods, all of their goods are exactly the same. There's absolutely no differentiation at all in perfect competition. If you wanted something different, too bad. All the goods are the same. And they're private. So there's no public goods. There's no club goods. There's no common resources. None of that stuff. It's all private goods. Frictionless markets, meaning transactions are costless. And more than that, you have perfect mobility of resources. So you can trade capital and labor between each other willy-nilly, and there's no real cost of doing that. Okay? So those are all assumptions that happen in perfect competition. Now we're going to take those beautiful assumptions and we're going to rip them apart. Not like rip them apart, but we're going to tenderly take them apart like a rotisserie chicken, and markets function perfectly. No hiccups found. I'm just going to write that little acronym up there, and then we're gonna assess them one by one in terms of what happens when this fails. Okay, perfect. What happens? I'm going to choose this one. All right, I'm going after homogeneous private goods. Actually, no, I changed my mind. I'm going after no externalities. Okay, what if there are externalities? What happens then? Well, if you remember from Econ 110, you have some situation where you can model this with some marginal private cost for the consumer and marginal private benefit for the, that's for the consumer, that's for the producer. And in theory, you're at some equilibrium right here, but that's not the real socially optimal equilibrium because you have some marginal external cost right here. Okay, some external cost that is not borne by this market, but it needs to be borne by this market. What's a way to do that? Well, an easy way to do that is you just take the marginal external cost and you add it on to your marginal private costs. There you go. That would take up this supply curve about that much. So it would shift it all the way over there. And there you go. You got your new equilibrium. You got a lower quantity, higher price, and you have internalized your externality. You can basically do that by doing a Pigouvian tax at the marginal external cost. And there you go. You're done. You could also do a cap and trade. If you did a cap and trade, you would, the socially optimal quantity, and you're going to, and assuming you can measure that and everything. So you're going to basically have a situation where it's going to look more like your supply curve is going to be normal like it was, but then once it hits that quantity, it's going to go straight up. So that's going to be more like what you'll observe in a situation where you do a cap and trade. Okay? So Pigouvian tax, cap and trade, all things that we love. And it just depends on the information that you have and which one is more efficient and which one is more doable. Okay? That's honestly all I want to say about externalities. I never learned that in 110 anyway. Well, I did, just in a different way. Anyway, so, okay. Externalities are not that hard in theory to understand regulating or correcting. So, all right, let's try this one. What if we go after many buyers and sellers with free entry and exits? Okay, what happens when this assumption breaks down? Okay, well, let's go to the simple case where we have, definitely don't have many, but we just have one. We just have one seller, a monopoly. Okay, so in this monopoly case, I'm going to draw several of these graphs because you never have too many L's in life. Okay, so in a monopoly, basically we all know how this functions. You have your demand curve, your marginal revenue curve, you got a marginal cost curve. They're going to produce right here, but they're going to charge right here, and you're going to have some deadweight loss. That is the classic monopoly scenario. I'll draw a few of these monopolies because why not? And don't be confused. that there are several monopolies here because we don't have several sellers. This is just different dimensions where there's one seller in each dimension. So this is first price discrimination. First degree price discrimination. This is how a monopoly might price discriminate, is that they would charge everyone equal to their willingness to pay. Okay, they're going to capture all of that surplus, and look how efficient that is. They got all of it. Perfect. All right, that's pretty simple. Okay, let's go on to second degree price discrimination. This monopoly is going to charge based on quantity. So you buy in bulk, you get a discount. Buy 100 products, we'll charge you a lower price. So maybe they'll charge a price right there for some people, and there's some consumer surplus, and there's some producer surplus. And then if you buy in bulk, they'll charge a different price to you right there. And they'll capture a little more producer surplus by doing that. Okay, second degree, pretty cool. I'm actually going to use both of these graphs for third degree, because third degree price discrimination is basically where you charge. I'm actually going to erase this one. You charge based on your characteristics of your market. And these different markets have different elasticities of demand. So here's one market with one elasticity of demand, but here's another market, and their demand looks different. You have divided up your consumers into two different markets. So you can charge one price for one market. There you go. And you can charge another price for another market. By charging two separate prices, you capture more surplus. And that is the idea behind third degree price discrimination. But wait, there's more. We're not done yet. There's also, let's talk about a monopoly. This looks very similar to the other ones, but in this monopoly, your marginal costs are actually pretty flat. Okay, it doesn't really cost you much of anything to produce more and more and more. Whoa, it doesn't. It does not. What the? Bruh. Okay, I don't know what I am on today. Okay, just imagine that line is straight, okay? So basically what they're gonna do, they have very flat marginal costs. And normally they could produce here and charge here and capture a lot of surplus, and that would be great. But a lot of deadweight loss, and there's consumer surplus, and they can still capture some of that. So here's how they're gonna do it. Basically, they're going to produce in a way where why did I say produce? Okay, basically they're going to capture all of this surplus by charging an entry fee to the entire market. Okay, so they will charge a fee equal to the area of this entire triangle, and then after that, they will charge price equal to marginal cost. Okay, so they're going to get no margins on these later products that they produce, but it doesn't matter because they've captured all of this surplus by charging an entry fee. So they find out the area of this entire triangle. Let's say that's 10,000. Okay, so 10,000 is the total entry fee that they charge. The entry fee per person is based on how many consumers there are. So let's say they have 100 consumers, and it's 10,000 over 100. So per person, they would pay $100 of an entry fee per consumer. Okay, and that is the idea behind two-part pricing or two-part tariffs, or whatever you want to call that. Okay, perfect. So that is all monopolies and everything and how they can price discriminate. And you see a lot of stuff happens when you just have one seller, not even talking about other situations yet. But, okay, we've talked about monopolies, but what if you have one buyer? A monopsony, okay? Not necessarily Sony the company, but well, actually, I don't want to draw that right now. I'm not going to draw that right now. But a monopsony is where you have one buyer, okay? So essentially, like you have a firm in some town, and they're the only firm that buys labor, okay? They're the only person that hires people. So they're going to, just like a monopoly makes decisions based on their demand curve, okay? Or not their demand curve, but the demand curve. A monopsony is going to take into account the supply curve, and they're going to make their decisions based on that. Okay, so it functions the exact same way as a monopoly, just like backwards, pretty much. And a lot of times, a response to these monopsonies, or sometimes a response to these monopolies, is unions. Okay, so you could have a labor union, and unions aren't always a response to monopsonies. So let's just examine unions separate from any other external conditions. So let's just say a union is examining. There is a wage demand curve, which is a function of labor, and a wage supply curve, which is a function of labor. Okay, and maybe you're at some equilibrium, maybe you're not. But a union is basically a monopoly unions it's more of a cartel because it's a conglomerate of people that are acting like a monopoly. So that's what a cartel is. That's exactly what a cartel is. So a labor union is basically, they could have a few goals, but let's say they want to maximize producer surplus. That's an understandable goal for a union. Okay, so producer surplus is going to be whatever, there might be some difference between demand and supply here, and they're going to maximize the area of their producer surplus, which is that trapezoid right there. Okay, so that is the union's maximization problem. Now, if they do this, then there are people here, there are workers that would be willing to work, and the firm is willing to pay them even higher wages, but they're not. They're unemployed. So it's not good for those workers, but it's great for the workers that get a higher wage that are part of the union's labor supply. Okay, so that's what happens when a union is maximizing producer surplus. Now they could choose to maximize employment, but notice if they maximize employment, they would just go all the way out here, and then you would just have your perfectly competitive outcome. So it's not very interesting if their goal is maximizing employment. That's what that would be. What else can they do? Oh, there's something else that they can do actually. If they don't want this deadweight loss and they want to capture even more surplus, what a union could do, they could charge every worker, they could have every worker be paid according to their marginal revenue product of labor, or their MERPL. This demand curve, I'm so sorry. This is a supply curve, this is the demand curve. Obviously. This labor demand curve, or wage demand curve, is same thing as MERPL curve, right? So if you hire every worker according to and pay them their MERPL, then, man, this guy gets a lot, right? But you're going to capture all of this surplus right here, and you're going to be in a really good spot. Okay, so you could do that. You could price discriminate. That is pretty hard though, paying absolutely everyone a different wage. I mean, realistically, there are ways to do it, I guess, but probably, more realistically, maybe they'll base their pay on seniority or something, and they'll have different kinds of workers or different levels of workers, and so they'll capture some surplus right there, and they'll charge another, pay another wage and capture more surplus right there, more surplus right there, something like that, right? But they will have some deadweight loss still, okay, and have those people unemployed. Or will they? Okay, so in a situation where you have a monopsonist, it could be a little bit different, because now I will draw the monopsonist graph. Okay, here's a monopsonist graph. Okay, looks exactly like a monopoly graph, but upside down. So they have some wage supply curve, right, as we do. And then over here, this is going to be the marginal expense of labor. And then they're going to have some MERPL curve, right? Some demand curve. Okay, so they are going to demand where the marginal expense of labor equals the marginal revenue product of labor, okay? But the wage they are going to pay is down here. See how this functions just like a monopoly, okay? So they're going to pay this wage, and there's going to be some deadweight loss. So notice that if a union negotiates higher wages, in the case of a monopsonist, you could end up in a situation where you have a higher wage, but you're actually hiring more labor at that higher wage as well. So, yes, like all else equal in a perfectly competitive setting, like this is the effect of a union, but you see how the effect could change if you're in a situation with a monopsonist. So, oh man, that stuff about unions and that's all great and everything. There's one thing about monopolies that we didn't touch on that I still want to touch on. It's a structure of monopoly that we forgot to talk about, which is the natural monopoly. So a natural monopoly has very high fixed costs. So their average cost curve is going to look like that, from a marginal cost curve that looks something like that. Okay, and then they will, have some, demand curve and some marginal revenue curve. Okay, so there's average cost, there's marginal cost. So they will produce, again, where marginal cost equals their marginal revenue. They will charge up here at the demand curve. But, okay, let's say you want to regulate this. And, well, shoot. I mean, there's supposed to be many firms with free entry and exit. Wouldn't it be better if there were more firms, right? Let's just get more competition in there for our natural monopoly. But since natural monopolies have super high fixed costs, I mean, look at their cost structure and their marginal cost being below that. So it's actually not more efficient in this scenario to have multiple firms. Actually, the most efficient thing is just have one firm in the case of a natural monopoly cost structure. So you want to stay with the one firm, whether they're producing sewer or gas or power or whatever they're producing, you want to stay with the one. Okay, so you could go, hey, perfect competition, let's charge price equal to marginal cost. But obviously, that's not going to work because you're under your average total cost. So your firm is going to lose money, and then they're going to exit the market, and that's going to be not good. Well, you could charge price equal to average cost, right? Which, that could work. You'll still get a pretty good quantity right there. But notice that they don't have incentives to keep their cost structure low. So they could just raise their average total cost. And if you're willing to subsidize them, I mean, you could subsidize them in both cases, right? You could subsidize price equal to marginal cost so you can get that quantity. You could subsidize when price equals average total cost, but they don't have, again, they don't have incentive to keep their cost structure low in that situation. So that's a trade-off there. You could say, let us say that your profits, okay, we'll enable you to have some fair profits, and we'll determine that by the ratio to your capital. Okay, so your ratio of profits to capital has to be, 6 or 7, all right, somewhere in that range, and you can't go above that. Well, what's this firm going to do? They're going to just buy more capital. They're going to overcapitalize. They're going to buy gold plating and put it on their capital if they have to, so they can reach this this ratio. And basically, it's going to be inefficient because they're going to have more capital than they need. Invest too much in capital and not enough in other things. So that's a trade-off there. All right, one last thing you could do is you could have a two-part pricing model. This is different than what we were talking about before. But basically, you're going to have like a really high price. Let's get this high price, and we're going to charge this price to one subset of consumers. And then we're going to set price equal to marginal cost after that. How about that? So we charge one high price, and what do we get? That's above your average cost. So you're making some profits from that. How do I evaluate my profits here? Your average cost between your yeah, there it is. There it is. Perfect. So that's your profits that you're going to get above your average cost curve by charging that price, and then you're charging equal to marginal costs after that. So then you're going to lose money on all of those. And obviously those areas aren't equal. So you'll want to try and balance that out if you can. But the essential idea is that you're trying to balance out, you're trying to reach the optimal quantity by balancing out profits. And again, in this case, you would have to subsidize anyway to keep them in business, or else they're going to exit the market. So we see that there are all kinds of trade-offs to the different ways that you could try and regulate natural monopolies, but because they're cost structured, it is pretty hard. But we're not here to talk about 380 stuff. Did you talk about them in 380? Maybe. That's just what can happen in a monopoly setting, but we actually want to go beyond that to, I guess we're done. Okay, perfect. That's natural monopolies. Now let's talk about what happens when, let's attack another assumption. Let's attack, no, actually, I changed, yeah. Let's attack this one. Homogeneous goods. What if we have free entry and exit? We have many buyers and sellers, right? We allow all of that. We just have differentiated goods. How would that look? Well, what you're talking about is monopolistic competition. So you have a bunch of firms that look like monopolies. Here we are again. Okay, and they're going to do the monopoly thing that they do, right? Let me put some average cost curves in here. Let me put an average cost curve right there. Okay, so they are going to make some profits, okay, in the short run. But because you have free entry and exit, there's nothing stopping other firms from saying, I want some of that profit, and then they're going to come into the market. When they come to the market, what's going to happen to your demand curve is it's going to shift. Okay, you're going to have this demand curve shift going on, And basically, you're going to end up at some point where your demand curve, there's your new marginal revenue curve. Basically, it's going to intersect. You're going to charge, some premium, so your price will be above your marginal cost. Sorry, I drew that so poorly. But your price is still above your marginal cost because you're a monopolist. But you can see that all of these firms entering the market has eliminated all of your profits. So your price equals your average total cost and your profits are zero. So that's what happens in monopolistic competition. What if you have differentiated products and there are many firms, there are not many firms with free entry and exit. Let's say there are entry barriers. Well, in that case, we can model differentiation maybe in a spatial way, okay? So this space or this distance right here measures the amount of differentiation between different products. So let's say you have A and B, these are different products and they're differentiated from each other. And you have a consumer right here that they really want a product, that's exactly how they want. But there isn't a product there. They have A and B, so they got to choose between A and B. And assuming they're just going to buy one of these products, then their choice is going to be based on a number of factors. It's going to be based on the distance or differentiation between what they want and the product they're going for, and how much that matters to them. We'll call that travel costs, okay, in this scenario, because we're talking about space and distance and everything. And it's going to obviously be based on the price of each product, A and B. And then a different consumer will be at some point where their cost of buying from A, or rather their utility of buying from A, is the same as their utility of buying from B. Okay, so that's how we might model differentiation, or we might model it in a circle. We've seen that before. So we see, here's several firms. There's A, B, and C, and they're differentiated from each other, also by distance, and you have consumers there. And you reach different conclusions with these models. So with these models, it's hard to talk about because there's a lot of assumptions that you can play around with in these differentiation models. But these are just introductions to how you might observe this concept of differentiation and think about it, because this is what people do, for example, in industrial organizations sometimes. But that is some ways we can think about what happens when you have differentiated products. Now, we've talked about a lot of stuff. Let's talk about essentially when we have these assumptions break down, what are some ways we can see that? Well, first, we can view a monopoly. Okay, that's pretty easy. That's when you have one firm in the market. Okay, we can view, we talked about monopsonies and unions, I guess. So, shouldn't have that. I won't write that in this list, but you have cartels, okay? So a cartel is when you have a bunch of firms and they just act like a monopoly. You can have production functions for each firm. You just add them all together, squish them together, solve it like a monopoly, and split the profits. So cartel is pretty much exactly like monopoly. Okay, you can have Cornell. What is Cornell? Cornell is where you have few firms that compete on price. No, sorry, quantity. They compete on quantity. And how is this solved? Well, when these firms compete on quantity, basically what they do is, let's say you have firm A that profit maximizes. So you profit maximize for firm A, and you get some quantity of firm A, and this is going to be because, again, their products are undifferentiated in Cornell. Undifferentiated products, there's some demand function for the whole market, right? So the quantity for firm A is going to be in terms of the quantity of firm B. So basically, my choice of firm A, my quantity, is going to be based on what firm B does, right? Oh man, let's take a look at how this would work. So this is called a reaction function. Okay, reaction function. Okay, so firm A is going to respond to what firm B does. All right. And we can do the same thing independently for firm B. So here is the profit maximization problem for firm B. They're going to have a reaction function in terms of what firm A does. They are strategic decision makers. We notice, let me highlight this, is that when you break down the assumption that there are many firms with free entry and exit, then you have people start to make strategic decisions that are best responses to what other people are doing. We should talk about that. We'll talk about that in a second. We absolutely will. But these are strategic responses called reaction curves, okay, or reaction functions. Okay, so when you get these and you get them separately, then you take one and plug it into the other, and that's how you solve for the quantity that A and B will produce. Okay, that's how Cournot works. Now Bertrand is very similar. Okay, you have few firms and they are competing on price. Okay, so it's actually solved the exact same way as Cournot. It's just instead of quantity, you're thinking about price. Actually, let me differentiate. So you have undifferentiated Bertrand, which is when firms compete on price, but their products are not differentiated. So really, they just compete on price all the way to the bottom until price equals marginal cost. So that is not very interesting. All right, so, or you could have differentiated Bertrand. And in differentiated Bertrand, this is where you would solve it like Cournot, because their prices are a function of the price of the other firm. They do compete on price, but not all the way to the bottom. They compete on price until some certain point based on, based on loyalty of their customers, how much they substitute to the other firm based on how they adjust their prices. So it's a little more interesting. So you solve it like you would Cournot, except your Q's are going to be P's. All right, but you plug one into the other one, it's simultaneous. Both of these are simultaneous. What if it was not simultaneous? Then you would have Stackelberg. Okay, Stackelberg is few firms that compete on quantity, but they do it sequentially. Okay, this is simultaneous, this is sequential. So how does that make Stackelberg different? Well, shoot, I should have gone over game theory first, okay? I'm about to go over game theory, don't worry. Just skip to that section if this doesn't make sense. But basically in Stackelberg, when you have a sequential game, we solve sequential games backwards. We use backwards induction, okay? And so we're gonna look at what firm B is going to do, and then we're gonna put that into firm A's decision. So what that means is that I'm gonna start kind of like Cournot. I'm gonna solve the maximization problem for B. I'm going to get the quantity for B in terms of what A produces. And now that firm A knows this, they are going to solve their own maximization problem, taking that into account. Okay, so I'm going to take this reaction function, I'm going to plug it in to the maximization problem for firm A. Then I will maximize. And then I will get the quantity that A will produce as the first mover. That is what makes Stackelberg different than Cournot. Cournot, you solve them independently, plug one into the other. Stackelberg, you solve one for the reaction function, plug the reaction function into your maximization problem, and then maximize. Okay? That is how Stackelberg works. And then we also talked about monopolistic competition, which is where, in the long run, price is more than your marginal cost, but it does equal your average total cost because of free entry and exit. Okay. These are all things that can happen, situations that can come up when you have breakdowns of either many firms with free entry and exit, or homogeneous products, or both. These are all studies of that, and the world of industrial organization deals with that. Okay, but you know what I did? I skipped game theory. Darn it, so I'll go back. And I will talk about how we make strategic decisions based on the reactions to what other people are doing. This happens when we have market power. When we have market power, now our decisions influence price, they influence other people like we just talked about, right? So we'll talk about the more general world of game theory and how we make strategic decisions and best responses to other people's actions. So, game theory. Here is a game. Looks very fun. I know. It's a normal game because it's written in normal form. Well, it's a normal form written game. Okay, so you have two players. You have A and you have B, and A and B both have choices. A can whip or nay-nay, and B can whip or nay-nay in tandem. All right? So A and B are going to look at each other's, A's payoffs are on the left. B's payoffs are on the right. And they're going to observe what they are going to do and what the other player is going to do. We're going to determine if there's some stable outcome that's going to come out of this game, that we can predict exactly what's going to happen, even though we have these four different scenarios. So let's look at A. If B whiffs, A is going to nay-nay. If B nay-nays, A is going to nay-nay. Oh, look at that. A has a dominant strategy to nay-nay. All right, they're going to do it no matter what. Let's look at B. All right, if A whips, B's going to whip. If A nay-nays, B's going to nay-nay. Okay, B does not have a dominant strategy. Depends on what A does, right? But okay, we notice that this depends. What was I saying? I don't remember. Anyway, we have some stable outcome that results from this. This is a Nash equilibrium. Okay, this thing right here. This is a situation in which neither player has incentive to deviate to something else. That's a Nash equilibrium. Okay, we can also write this game in what's called extensive form. So let's write player A up here that has the options to whip or nay-nay, and then player B has the option to whip or nay-nay, and if they both whip, we get 4-3. A whips, B nay-nays, then we get 1-2. And if A nay-nays and B whips, we get 5-1, and then 3-4 if they both nay-nay, right? Cool. Okay, so this is the game written in extensive form. I've drawn a circle around B because that means that this is a simultaneous game. They make decisions at the exact same time. Man, I wish I had explained that before I went over those Stackelberg and Cournot things, but that's okay. Anyway, so this is A making decisions, this is B making decisions, and it's a simultaneous game. But if I remove the circle, this means it is a sequential game. And in a sequential game, as we discussed, A moves first, and then B observes what A does, and then moves. Okay? So when we see B moving, we are going to solve this game backwards, as I discussed in Stackelberg. It's how we solve Stackelberg, right? So from B's perspective, in this state of the world, what is B's better payoff? We're going here, right? If B is going to whip. In this state of the world, what's B's better payoff? The 4, right? B's going to nay-nay, okay? Now, we know what B is going to do in each state of the world. Now we look at the perspective of person A. From person A's perspective, okay, if I go here, B's going to whip, and we'll get 4-3. If I go here, B's going to nay-nay, and we'll get 3-4. 4 is better for A. So A is going to whip this scenario. And we observe that this subgame perfect Nash equilibrium that we have discovered by backwards induction is actually different in this scenario than the pure strategy Nash equilibrium that we found in the simultaneous game, okay? Having it be a sequential game in this case has changed what the outcome will be, all right? But I said this was a pure strategy Nash equilibrium. What does that even mean? What does that even mean, okay? I'll tell you what it means. It's different than a mixed strategy Nash equilibrium, which is, you know, I thought that was pretty straightforward, but let's talk about what that means. Essentially, let me change these payoffs a little bit. Change it to something like this. Even right? Sure. Okay, so let's try to solve this game. So, from the perspective of A, if B whips, then A is going to whip. If B nay-nays, A is going to nay-nay. Perfect. If A whips, B is going to nay-nay. If A nay-nays, B is going to whip. Ah, interesting. And now we have this sort of windmill fashion thing, and we see that there is no point in this game where neither player has an incentive to deviate. In other words, someone always has an incentive to deviate to another option. So we have not found a stable outcome. We haven't found a Nash equilibrium from this. Does that mean there's no Nash equilibrium? Well, not exactly. What if, as player A, I could probabilistically play and mix up my strategy in such a way as to make B indifferent in the strategy they play? In theory, these players can play with different probabilities of choosing each option, and we could, in theory, reach some point where playing with those probabilities produces a stable outcome in terms of their strategies. How do we even solve that? Well, we could, there's a couple ways. We could say that the expected payoff, let's say, what makes B indifferent? I'm player A. What makes B indifferent? Well, actually, let's say I'm player B. I like that better. I'm player B. What makes A indifferent? Well, A is indifferent if the expected payoff from A expected payoff from A whipping is equal to the expected payoff from A naying, right? Then A is going to be, by definition, indifferent between whipping and naying. There's another way to solve this. I'm going to show the more complicated way for, what do they call it? Pedagogical purposes? For pediatric purposes, I'm going to show that, I'm going to show the more complicated way of solving it, which is that you can maximize, if I'm player B, and I'm looking at what makes A indifferent, then if I assume that A is going to maximize their expected payoff, their total expected payoff from their strategy, then they're going to be at some point where they're not going to tilt more towards whipping or towards naying. So this is the intuition behind this concept, that I'm going to look at A maximizing their expected payoff. All right, let's see. What is the expected payoff of A? Well, let's take each of these situations. So the expected payoff of A, in the case where, we'll say there's a probability that A whips and a probability that A nays, which is 1 minus the probability A whips. There's a probability that B whips, and there's a probability that B nays. Okay? Perfect. So the expected payoff of A is equal to, I'm going to take that max out. Well, no, let's leave the max in. Okay, the expected payoff of A is 2 in the situation where they both whip. So that's A whip and B whip. It's going to be, what's the expected payoff? We're still solving expected payoff. It's 0 in the case where A whips and B nays. Okay. It is 0 in the case where A nays, where, oh my gosh, B whips and A nays. And then, when they both nay, it is 1. Payoff is 1 when they both nay. Okay, perfect. Now let's try to make this a little simpler here. So we have, what is that? 2. Yeah, those cancel out, obviously. And we have the first term plus, okay, 1 minus probability B whip minus probability A whip plus probability A whip, probability B whip. So what is that? 3 probability A whip, probability B whip plus 1 minus probability B whip minus probability A whip. Did I do that right? Let's find out. So we're going to try and maximize this. And so what can A choose? We're looking at A's maximizing their expected payoff. Okay, so they are going to choose the probability that they whip, right? The probability that A whip. So that's what we're going to maximize as. And so we're going to get 3 probability B whip minus 1 equals 0. 3 probability B whip equals 1. Probability B whip equals 1/3. Okay, this is what we found. That in order to make A indifferent between whipping and naying, then B will have to whip with the probability of 1/3. That is B's strategy to make A indifferent. And if we solve the same thing for A, we would get that the probability of A whipping would be 1/2 to make B indifferent. So if A whipped with a probability of 1/2 and B whipped with a probability of 1/3, we would be in a case where neither player would have incentive to deviate. And thus, we found a mixed strategy Nash equilibrium. Perf. Okay, let us change these payoffs again. One more time and look at another scenario. This scenario, okay, we have 3, 3, 4, 0, 0, 4, 1, 1. All right, let's try to solve this game. Okay, from the perspective of A, if B whips, then A is going to nay-nay. If B nay-nays, then A is going to nay-nay. Oh, dominant strategy, nay-nay. If A whips, then B is going to nay-nay. If A nay-nays, then B is going to nay-nay. Ah, they both have a dominant strategy to nay-nay. Interesting. Okay, so did I solve that backwards? whatevs. A goes, if B whips A, yeah. I solved that. Solved that right. If A whips B nays. Yeah, it's right. It's all right. Okay, so this is our Nash equilibrium. Okay. Notice that that is not the best outcome for both players, right? We could be at 3-3, right? A could get 3 and B could get 3, right? But we're not there because they both have a dominant strategy in nay. And if they were at the 3-3, then they would both try to go for the 4, and thus we end up at the 1-1. Socially optimal outcome, but this is the Nash equilibrium outcome. This is called the prisoner's dilemma. A very classic prisoner's dilemma game right here. And okay, well, how can we improve this, right? What if we cooperate? Let's say, hey, B, player A comes to player B, says, what if we cooperate? We'll both go for 3-3. He's like, okay, let's do it. Well, as soon as you cooperate and you know the other person's going 3, you're obviously going to deviate and you're going to try to go for the 4, right? I mean, it's just going to happen. The payoff is higher. So that's how we define the game. So what if it was for 3 time periods? What if we're like, okay, we'll play this 3 times. Let's cooperate 3 times, okay? Well then, what's going to happen in the last time period? As player A, I'm going to say, well, I would rather have 4 than 3. So in the last time period, I'm taking the 4. Oh, but B knows I'm going to do that. And so B is going to deviate in the second to last time period. But I know B is going to do that, so I should just deviate in the third to last time period. See, we should just deviate now. And even if you have 100 times where you play this game, any finite number of times you play the game, cooperation is not sustainable for that reason. They're going to use backwards induction and they're going to deviate earlier. So, but what if you play for an infinite number of time periods, right? Okay. So you're going to play this game and you don't know how long you're going to keep going or when it's going to end or if it's ever going to end. So that makes things a little more interesting because then you can examine what is your expected payoff. Let's take, either player, doesn't matter. What is your expected payoff from cooperating? Okay. And what is your expected payoff from deviating? And when those equal each other, that's going to be your indifference condition between cooperating and deviating, right? This is going to be based on your discount factor. The discount factor is how much you value a future time period. So I would rather have $1 today than have $1 tomorrow. So there is some discount factor I apply to $1 tomorrow that I can multiply it by, and that is the net present value of tomorrow's dollar today. Okay, so let's say that let's solve for the expected payoff of cooperating. I'm going to get 3 in the first time period. In the second time period, I'm going to get 3, but I value it at some discount factor, right? I'm discounting it based on my discount factor. Okay, in 2 time periods, I'm going to get 3, but then times the discount factor times the discount factor, okay? So this is actually going to go on forever, right? This is the value of cooperating. And we can actually solve this because this is a well-known series from Calc 2. This is a geometric series, okay? And it's the sum of n equals 0 to infinity of a delta to the n, okay? And we know from math that that converges to 1 over 1 minus delta. Sorry, it converges to a over 1 minus delta. Our a in this case is 3, so we know that this value is equal to or converges to 3 over 1 minus delta. That is what we get from cooperating in infinity. All right, what do we get from deviating? Well, we would get, in the first time period, 4. The second time period, though, we're back at the Nash. So this is assuming a Grimm trigger strategy, by the way. Grimm trigger meaning that you're saying, okay, let's cooperate, let's collude. But as soon as you don't collude anymore, I'm done. We're at the Nash forever and ever and ever. No forgiveness, okay? So with that strategy, we know you're at the Nash forever. So it's 1 delta, and then I get 1 delta squared the next time period, and on and on and on forever. Now, I would really like to converge this, but I do need an extra term in front of there because of how a geometric series is defined. I need a 0 term. So I'm just going to split this 4 into a 3 plus 1, and now I can use the 1 and converge this series. And so I end up with 3 plus 1 over 1 minus delta. All right, now I would like to know what my delta should be. How patient do I have to be, basically, in order to cooperate, for it to be more valuable for me to cooperate than to deviate. So let's solve that. That would be, we're going to set 3 over 1 minus delta equal to 3 plus 1 over 1 minus delta. These payoffs are equal in this situation, right, when I'm indifferent. So that would mean that this is what? 2 over 1 minus delta equals 3. So 2 equals 3 minus 3 delta. 3 delta equals 1. So delta would have to equal 1/3. Or in other words, I have to be at least, my discount factor should be at least 1/3 in order for me to cooperate. Otherwise, not cooperating. It's not worth it. Okay? So that is how you would solve an infinite game. There's actually an easy like shorthand way to do this, which I kind of like, which is where your delta has to be greater than or equal to your payoff of deviating minus your payoff of colluding. And these are first time period numbers right here, over your payoff of deviating minus your payoff of Nash. Okay, so you can just solve this with first period numbers and you don't have to use the geometric series technically. So then your payoff of deviating is 4, payoff of colluding is 3, payoff of deviating is 4, payoff of the Nash is 1, and you get 1/3. Needs to be what your delta is greater than or equal to. Okay, so that is infinite games, and you can sustain collusion in those scenarios. All right, well, yeah, that would have been a great thing to talk about before Stackelberg and Cornell, huh? Hopefully that still made sense because I'm not redoing it. Okay, we've talked about a lot of things. We're not done with our assumptions. Let's talk about what happens when this assumption breaks down. Perfect information. What if we don't have perfect information? What happens then? You could have a couple things happen. First of all, if you don't have perfect information about the characteristics of individuals, you could have a high-risk person that knows they're high risk, but you don't know they're high risk. And you can have an unbeneficial, inefficient transaction happen between you because of that. It's called adverse selection. You could also have a situation where you make an agreement with an individual, and then their behavior changes because they're protected from the consequences of their actions. And you can't monitor that, and so that's not beneficial for you. That's also inefficient. That would be moral hazard. That would be a moral hazard if that happened. So let's stop talking about those in the abstract and actually talk about insurance. Is an easy way to talk about this. So we'll talk about insurance. Okay, so let's say from an insurance company's point of view, let's say somebody has a probability of, use pi for probability, of getting into an accident and a probability of not getting into an accident. Which is actually just 1 minus the probability of getting into an accident. Okay, so from an insurance company point of view, they have some expected payout. Okay, some expected payout. If you get into an accident, they will pay you $100. But their expected payout is going to be 100 times the probability you get into an accident. But in the case you don't get into an accident, well, they're going to pay out 0. Okay? So that is going to be their expected payout. It's going to be how much they pay out times the probability of that situation. Okay? Because that's how we do expected value. All right, so in this case, actuarially fair insurance would be a situation where the insurance company has 0 profits. Or in other words, they charge some premium that's equal to their expected payout. In other words, it would be equal to that right there. If they charge that premium, this is actuarially fair insurance. They would make 0 profits in this scenario. So sad. That's just how it goes. All right, but now let's look at the perspective of the consumer. What premium would make the consumer want to buy insurance versus buying no insurance? That depends on the consumer's risk profile. It depends on the utility function, I should say. So let's say that this is your wealth and this is the utility you get from that wealth. Then a risk-neutral individual would just have a straight line. Like the more wealth they got, then they would get the exact same amount of utility from that wealth wherever they were on this curve. But we typically observe that individuals are more risk averse, meaning their utility functions look more like that. They get diminishing marginal returns from having additional wealth. Okay, so this is a risk averse individual. And so in this situation, this person has, they get into an accident. Well, let's say they don't get into an accident, then they keep the wealth that they have now. But if they do get into an accident, then they lose a good amount of their wealth. Let's fix this. So, you know, they're like right there. To make this more obvious, I'll make this. There we go. Okay, so let's say their probability is, you know, 50%, right? The expected payout of the insurance company would be $50. That's what they charge for their premium. And for this person, you know, their expected wealth would be somewhere around there, right? That is their expected wealth, because they don't know if they're going to get an accident or not. But notice that the utility level of that expected wealth is actually equal to this point on their utility curve where they would have less wealth. Why is that? Well, because they would prefer having this amount of wealth for certain rather than have this amount of wealth maybe, okay? They're risk averse. They don't like the risk. So this is what we call the certainty equivalent. All right, that's how much you would have to pay them for certain. Because, you know, maybe their expected wealth is $120, but if you paid them $100 for certain, they would be just as happy because they have no risk involved with that 100, whereas there's risk involved with the 120. So that's what a certainty equivalent is. And they would be indifferent to a bet of some sort, or a probabilistic scenario, if their certainty equivalent was equal to the expected utility of that bet. All right. Now, let's go back to this premium scenario, now that we know a little bit about this theory behind risk-averse individuals. Now, we are going to examine some premium. Let's say let's take no insurance. If they have no insurance, what is their expected utility? Assuming this is log W. Right, that's their utility function. Well, their expected utility in the case of no insurance, let's say they have $300. If there's $300 to start with, and $200 if they get into an accident, right? They lose $100 if they get into an accident. So their expected utility is going to be the probability they get into no accident times log 300 plus probability they get into an accident times log 200. Okay, so that is their expected utility in no accident. With no insurance, Now, if they do have insurance, yes, insurance, then their expected utility is going to be some function of the premium. Now, in these cases, if they get into no accident, so we observe actually that the payout for this insurance company is $100, and they lose $100. The consumer loses $100. So really, they're getting full insurance, meaning their wealth is going to stay at $300 whether they get into an accident or not. This is full insurance. They could also have partial insurance, but we're just looking at full insurance in this case. So if they don't get into an accident, then it's going to be log 300. And if they do get into an accident, it's going to be log 300. So really, their expected utility is literally just log 300. Okay? So that is their expected utility if they have insurance. This is their expected utility if they don't have insurance. And so we would set these, if we wanted to know that, oh, my bad, it's not just 300 because they're paying a premium. Obviously, they're paying a premium. It's 300 minus the premium, which is Z. Okay, log 300 minus Z. Log 300 minus Z. Okay, they're paying some premium. So we would set this equal to this, and then we would find out their indifference point between buying insurance and not buying insurance. Well, no, we set them equal to each other, and we find a Z, the premium at which they'd be indifferent between buying insurance and not buying insurance. Okay, so that's how you'd solve a problem like that. Okay, but what does this have to do with imperfect information? Because all these people obviously have perfect information in these scenarios. So let's, enough with all that. Let's talk about what happens with a perfect information breakdown and a situation of adverse selection, where we have an insurance company that does not know the difference between high-risk individuals and low-risk individuals. Here's your wealth in the case of no accident. Here's your wealth in the case of an accident. Now, in the scenario of full insurance, your wealth is the same whether you're in an accident or not. So we would represent that with a 45-degree line right down the middle there. That's the full insurance line, where your wealth in terms of an accident is going to be the same as your wealth in the case of no accident. Okay? Now, we have the full insurance line. We have some characteristics of individuals. These individuals are similar in the case where if they don't get an accident, their wealth is here. And if they do, they have a little less wealth. So let's say they're about right there. Okay? So they're similar in that regard, but these individuals are different because some of them are high risk and some of them are low risk. And high risk individuals are going to have a different actuarially fair insurance line than low risk individuals. Okay? Because their risks differ. All right, so there are their insurance lines. They're actuarially fair insurance lines. Okay? The goal of an insurance company is to find out how to find out who is high risk and who is low risk. Because they could just pool all of them together, the high risk and the low risk people, and charge them one premium. And what would happen if they had a pooling equilibrium? Then high risk people would pay less than they should, low risk people would pay more than they should, and ultimately the low risk people would take a different offer as soon as it was offered to them, because they would want something more. The low risk people would exit the market, and the insurance company would just be left with high risk people, which would be very bad for business. Okay, so that's why a pooling equilibrium is not sustainable. Okay, so they need some kind of separating equilibrium where these people, even though the insurance company can't observe whether they're high risk or low risk, we need some way to have them naturally sort themselves out. So we can do that. We can do it very magically. All right, so here is how we might engage in that sort of thing. Okay, so let's say the high risk people's indifference curves. Let me see if I can draw this correctly, because I never do. So their indifference curves are going to look like something like this. All right, they're going to be kind of flat, and something like that. Okay, so these are the high risk people's indifference curves. Okay, then we have the low risk people's indifference curves, and they're going to look, something more like that. Okay, these are people with different characteristics. All right, so their indifference curves look different. As an insurance company, how do I offer two bundles of insurance and have them self-select? Here's what I'm going to do. I'm going to offer this bundle of full insurance to people, or they can choose this bundle of partial insurance. What's going to happen in this scenario? High-risk people, are they going to prefer the full insurance bundle or this bundle? Look at this. The high-risk people prefer the full insurance bundle. So high-risk people will choose the full bundle. And low-risk people, they actually prefer the partial insurance bundle. Okay, because they're lower risk. They don't need full insurance, but they would prefer partial insurance. Okay, so they offer different bundles at different prices, and high-risk and low-risk people self-select based on their utility functions. And there you go. That's how you have a separating equilibrium. Now you could have a situation where they buy insurance, but then let's say that the probability of them getting into an accident was some function of this S is the amount of precaution that they take. So you take some precaution to prevent getting into an accident. But let's say you get full insurance, and now all of a sudden it doesn't matter whether you get into an accident or not because you have full insurance. So your precaution is going to go down. Your probability of getting into an accident is going to go up. That is a moral hazard problem. Okay, so you can try to fix that by maybe trying to monitor the amount of precaution people take. You could, you have copays, you have deductibles. You could, offering partial insurance is another way to counter that. But that's a real moral hazard problem that insurance companies have to deal with. What else? What else do they have to deal with? Actually, let's go on to adverse selection. Adverse selection can also be seen through a signaling lens. So let's say I want to signal as a consumer that I am a low-risk individual, or I am, a good worker. If I want to signal that I'm a good worker, then this is, a condition that has to be met. If I'm a good worker, then there has to be some cost of signaling I'm a good worker, and that cost has to be less than the cost of a bad worker signaling that they're a good worker. Right? Like that just makes sense because I'm a good worker, so it's easier for me to show I'm a good worker than for someone who's not to show they're a good worker. But something else that needs to be true is that the payoff of being a good worker, we'll call this this could be seen as like a wage. The difference in the wage between good workers and bad workers has to be such that it's worth me signaling. In other words, the cost of me signaling has to be lower than the wage increase that I get. Yeah. But that has to be less than the cost of signaling for someone who's a bad worker, because otherwise everyone would signal and then signaling wouldn't mean anything. Okay? So that's the concept behind signaling. And then the last perfect information thing that I might talk about is the Stigler search model. The Stigler search model actually goes into breakdown of frictionless markets, and which means costless transactions, right? But in the Stigler search model, you don't know all the prices in the economy, and you're searching. You're searching for a lower cost good. And every time you search, it costs you. So you have costless transactions are out, right? All your transactions, they have costs because you have to search. And you're going to keep searching, but not infinitely. You're going to search until you find something that is good enough. Okay? So that's the Stigler search model concept. Those are all things that relate to perfect information breaking down. What happens when we have imperfect information? All right, well, what else should we talk about? You know, we've addressed the breakdown of all of these assumptions. You could go more in depth into all of those, but there's one more thing I want to talk about before ending, something that perfect competition still does not really give us. And that is intertemporal decision-making, or decision-making over time periods in the future. Because perfect competition is generally a pretty instantaneous thing. And so one way that we might look at intertemporal choice is with the McCall Job Search model, which just says, let's say I live, I can live with my parents, and they can give me benefits equal to 40K. Perfect. Or I could take a job offer, and that job offer could give me benefits equal to 50K. Okay? But I could not lock into that job offer, and instead I could wait. If I didn't lock into this, and I waited till the next period, then, maybe there's a 40% chance that I get 40K as a job offer, and a 60% chance I'd get 70K as a job offer. And I want to know the value of accepting and rejecting that job offer. This is also based on my discount factor. This is another discount factor problem. So the expected value of accepting the job offer is going to be equal to 50K in this period plus delta 50K, that's the next period, plus delta squared 50K, assuming that we're taking forever into account here. And the expected value of rejecting that job offer is going to be 40K in this period plus, okay, so now I have to deal with, expected value in terms of probabilities. So that's going to be 0.4 times 40K plus 0.6 times 70K. Okay, that's the value of this other job. And that's going to be at delta, but it's also going to be at delta squared and delta cubed and on into infinity. Right? So in these cases, if I wanted to find the delta, that would make me indifferent because that's our unknown here. I would set these equal to each other. But you could see a situation where, maybe you know your delta, but you don't know the probabilities of these jobs. So what probability would make you indifferent? Or you could say, maybe there's only one job offer in the future, but what is the amount that they would have to offer you in order for you to take that wage? That would be like a reservation wage, is what it's called in the McCall Job Search model. So that's how the McCall Job Search model works. We also have other intertemporal models. We could talk about saving. The way that savings works, let's say that you have, utility function is the log of your consumption. But that is true over your entire lifetime. Okay, so you have, let's just talk 2 time periods. You have consumption 1, and you have consumption time period 2. And you also have savings in each of those time periods because you have earnings in time periods 1 and earnings in time period 2. Your savings is your earnings minus your consumption in that time period. But you have some some market rate, interest rate, at which you can invest your money and get a return on that money instead. So it's like you have this other discount factor. This is discount factor in terms of, for your consumption and earnings in terms of the market rate, which is just 1 over 1 plus R. Okay, mathematically, that is how you would discount and get net present value according to the market rate. So you're maximizing utility problem, you would want to maximize, you're smoothing your consumption really over these time periods. Maybe you'll save, maybe you'll borrow in terms of what your earnings are this time period and next period. But you're going to maximize your utility, which is log C1 plus delta, this is your discount factor, log C2. Okay, so you're maximizing this. This is your utility. And you're choosing what consumption in period 1 and period 2 to have to maximize that. But it's subject to some budget constraint. And your budget constraint is going to be you're going to consume all of your income over your lifetime. Not necessarily in period 1, but over your lifetime, you're going to consume all your income. That's typically the assumption we make with budget constraints. So earnings in period 1 plus your market rate discounted earnings in period 2 equals consumption in period 1 plus market discounted consumption in period 2. This is your budget constraint. So that is how you would set up a constrained optimization model for your savings. And then you would find out what you would save. Okay? Perfect. And what you would consume. Let's talk about 2 other models and then we'll end. First is an asset pricing model where you could buy an asset for some price today, and what is it worth in the next period? Well, it's worth, you can get rent from it. Okay, perfect. You get rent in that period, but it also depreciates based on what you paid for it, but you can also sell it for some price in the next period. But that's also discounted by 1 plus R plus the depreciation rate. That's how we're discounting this asset that you buy. So this is pricing for a durable asset. And we can keep going into future time periods, P1 and R1, and we can do this recursively. And we can essentially get that for an infinite number of time periods, the price that we would be willing to pay for this asset would be equal to the sum from 1 to infinity of the discounted rents that we can get from this property, from this asset, this house, whatever you want to call it. Okay. So that is the main theory behind asset pricing. I'm assuming here that rents start in period 1. Some people assume that rents can start in the initial period. It depends. So I would check with your instructor on that one. Okay, one more model. Let's talk about finite resource pricing. You are a firm, you have access to some finite resource, and the quantity demanded of that resource in time t is going to be 100 over the square of whatever the price is in that time period. Now, in order for me to sell the resource in this time period, it has to be true that the price in this time period, let's say we're in time period 0, is equal to delta times the price in the next time period, right? Because if this wasn't the case, like let's say that the delta P1 was higher, then I would just wait. I wouldn't sell in this time period. I would just save it, and I would sell it next time period. So we have to have that condition, and then obviously we know that the total quantity, the finite resource, which is usually given, is going to be the sum of all of our quantity demanded in each time period. We're gonna sell all of it. Okay, and with these 3 equations, we can solve. I mean, it's pretty easy. You plug your QT in here, then that's going to be in terms of PT. So you can solve this for. Let me make that multiple time periods. So you have PT, that's easy. You can just divide by delta to the t there and plug in for PT. And then you just have it in terms of P naught and delta to the t. And then you solve for P naught and you get what P naught should be in terms of delta, right? So that is finite resource pricing. And honestly, that's all I want to talk about for 382. That is an overview of all the concepts covered. I would say there's a lot there. But here's what I would say the main takeaway of 382 is, okay? There are a lot of assumptions to perfect competition. And achieving efficiency is actually really hard because usually those assumptions don't hold in the real world, okay? But we can model these frictions. And by modeling these frictions, we can understand them. And by understanding them, we can design smarter contracts and develop better policies because we understand these things. And that serves as the jumping off point for all of these other areas to go into, like labor and health and public and IO and all these different areas of economics where you understand these market frictions that affect the world today. Hopefully this was helpful. Like, subscribe, comment on I love dogonomics or Stephen is cute or something like that. And guys, I will see you next time.